So here's how we're going to now use the normal distribution to actually arrive at some probabilities. We're going to verify that the situation we're looking at is a binomial distribution. So we're going to find our n, p, and q values. We're going to determine whether we can use the normal distribution to approximate x, the binomial variable. And remember, that means we're going to check to see that n times p is greater than or equal to 5, and n times q is also greater than or equal to 5. If that is the case, then we can use the shortcut formulas for the mean and the standard deviation. We're going to want to apply the appropriate continuity correction, as we just saw above, and then there's two more steps. We just locate the z-score in order to find the probability for a z-score. This is where we use our standard normal table. And I guess it's worth putting in here, if you don't remember your z-score formula, it's the score that you're converting minus the mean divided by the standard deviation. So let's put this all together now. In example 3, we're again looking at the 8 to 18-year-old heavy media users in the US, and we're selecting 45. Now notice there's this question at the end here. What is the probability that fewer than 20 of them respond yes? So because the responses are yes and no, this is going to be a binomial probability distribution. My n, my total number that I'm selecting, is 45. My probability of success that they say yes, they do get fair or poor grades, was 0.47. Remember, q was 1 minus that value, or 0.53. And if we hadn't learned this idea of approximating with a normal distribution, if we want the probability that fewer than 20 respond yes, we'd have to let x be 0, 1, 2, all the way up to 19, and we would have used this formula ncx, p to the x, q to the n minus x. And again, having to do that 20 times would take forever. So this is the power of using the normal approximation. But first, we need to check and make sure that we can. So I need to check n times p and n times q. We've already done those calculations previously, so I just brought them over. And remember, these are both greater than or equal to 5, meaning we can proceed with the normal approximation. So the next step is to identify your mean, which is n times p. So the mean in this case is 21.15. And the standard deviation, remember, was the square root of n times p times q. And again, we already previously calculated that to be about 3.35. So all these steps we've done before. What's new now is we're going to pick up with a continuity correction. My binomial probability that I'm looking to calculate is for fewer than 20. In symbols, I want my x value to stay below 20. I now want to convert that to a normal distribution probability. And in this case, they do usually want you to sketch the actual normal distribution that you're using to approximate. So rather than just drawing the number line, I'm actually going to draw the distribution with these characteristics. The mean is always the middle of the normal distribution. So at 20, I'm going to put 21.15 in the middle of my number line. That's going to be where my line of symmetry and my peak are located. And then my standard deviation is 3.35. So I'm going to add that as I move to the right. So if you add that on to 21.15, you get 24.5. If you subtract it from 21.15, you get 17.8. Within the first standard deviation, the curve is curving downwards. When you get to that first standard deviation, then it starts to curve upwards. So, in other words, this is approximately what my normal distribution looks like. If I want x to be less than 20, I want to think about where 20 is on my number line, which is going to be closer to 21 than to 17.8. So now, if when I want to convert x is less than 20, x is not allowed to equal 20. So the first value it could take on that's a whole number is 19 and under, which are these values. But remember, my continuity correction says I also need to consider any decimals that are going to round to 19, namely those that are bigger than 19 up to 19.5. So my equivalent normal probability would be x being a number less than 19.5. Now I'm going to stop and find the z-score for this particular value. So to find the z-score for 19.5, I do the score minus the mean divided by the standard deviation. And with the standard deviation, again, do not use the rounded 3.35. You always want to take your original calculation, which was the square root of 45 times 0.47 times 0.53. Again, don't use rounded values. And you will get approximately negative 0.49. Now, always round that to 2 decimal places because that's the number of decimal places in our standard normal table. I have calculated the z-score. I can now change my probability statement to say, if I want the probability that x is less than 19.5, that's the same as the probability of the z-score being less than negative 0.49. And now you're at the point where you would just go to your standard normal table, look up negative 0.49, and get the 4 decimal place probability. And it turns out to be 0.3121 when you do that. And written as a percent, that's 31.21%. So going back to our question, what's the probability that fewer than 20 of them respond yes? It's going to be about 31%. And again, I was able to do this without having to calculate 20 different probabilities. In the next example, we're looking at a study on aggressive driving that found that 47% of drivers say they've yelled at another driver. If we randomly select 200 drivers in the US and ask them whether they've yelled at another driver, what's the probability that at least 100 drivers will say yes? So again, this is a binomial probability distribution because they're going to either respond yes or no. So I want to consider my variables. N, my total sample size is going to be 200. My probability of success that they say they have yelled at another driver was 47% or 0.47. My probability of failure, or a person responding no, will be 1 minus that value, which is going to be 0.53. And again, rather than having to let x take on every single value from 100 up to 200, if I check my calculations n times p and n times q, and they're both bigger than or equal to 5, I can use the normal approximation. And since both of these values are greater than or equal to 5, we can use a normal approximation. Once we know that we can use the normal approximation, we're going to use the formula for the population mean, which is n times p, which we know is 94. And for the standard deviation, it's the square root of n times p times q. And if you type those in and take the square root, you're going to get approximately 7.06. So next, I'm going to picture my number line, but again, remember, instead of just a number line, I'm actually going to draw my normal distribution. The mean is 94, so that should be the center of my distribution. I'm going to add one standard deviation to the left, which would get me to the value 101.06. I'm just adding 7.06. And then in the other direction, I'm going to subtract that amount, and that puts me at 86.94. So my curve will have a peak at 94, curve downwards to the first standard deviation, then up, curve down, and then up. My binomial probability that I'm looking for is the probability of at least 100 drivers saying yes. At least 100 is the probability that x is greater than or equal to 100. I need to convert that now to a normal distribution probability. Well, if x has to be at least 100, I'm going to find where 100 is, which is going to be closer to 101. So we'll say maybe right here. So my probability is supposed to be equal to 100 and up. And then I want the continuity correction that allows for the numbers that round to 100. So those would be beginning at 99.5. Anything bigger than 99.5 would round to 100. So my equivalent normal distribution probability is x can be anything bigger than 99.5. Now I want to take and find the z-score that corresponds to 99.5. So I take that score minus the mean, which is 94, divided by the standard deviation. And again, you're going to want to go back to the square root of n times p times q. And you'll get a z-score of approximately 0.78. So now I can write my probability in terms of a z-score by saying if I want the probability that x is greater than 99.5, that's the same as the probability of the z-score being greater than 0.78. However, you have to be careful right here. Remember, your standard normal table is set up to give probabilities for z-scores less than a certain number, not greater than. So we'll have to rewrite this probability as 1 minus the probability that z is less than 0.78. And we're doing that again because when we look up values in the table, we get the less than. So to convert it to greater than, we just subtract from 1. So if you look up this probability in your standard normal table, you're going to get the decimal 0.7823. Now just subtract that from 1, and you get 0.2177, which is the same as about 21.77%. So that's the probability that at least 100 drivers will answer yes. All right, now I'm going to go through one more example, but a little bit more quickly here. We have a study of NFL retirees ages 50 and older, and it found that 62.4% have arthritis. We're going to randomly select 75 retirees who are at least 50 and ask whether they do. What's the probability that exactly 48 will say yes? Again, this is a yes-no situation, so this is a binomial probability with n being 75. Probability that they report yes is 62.4%. And if you move that decimal place over 2 places to the left, you get 0.624. Probability of failure would be 1 minus that number, which gives me a Q value of 0.376. Now test to see if we can use the normal approximation by performing these two calculations. Here are my results, and these numbers are both greater than or equal to 5. Therefore, I can proceed with my normal approximation. I begin by finding the mean, which is already done, and the standard deviation using the formula square root of n times p times q, which should give you approximately 4.19. Next, sketch the distribution. I've set up my distribution, and my binomial probability that I am trying to calculate this time is the probability that exactly 48 people will say yes. So that's the probability that x equals 48. I'm going to convert that to a normal distribution probability by thinking on the number line. I locate where 48 would be, which maybe is right about here. And because I need to apply my continuity correction, I need to consider all the numbers that are actually going to round to 48 by going half a unit below and half a unit above. So when I do that, half a unit below puts me at 47.5, and half a unit above puts me at 48.5. If I want to calculate exactly 48, I'm looking to calculate between these two values. So this probability is equivalent to 47.5 less than x less than 48.5, or in other words, that x will be a number between 47.5 and 48.5. In this case, you're going to need a z-score for each of these two values. I've set up my z-score formulas, and 47.5 should give you approximately, to 2 decimal places, 0.17. 48.5 should give you approximately 0.41. So my normal probability can now be expressed in terms of a z-score probability, and that would be that the z-score is something between 0.17 and 0.41. Now, in order to calculate a between probability, this is going back to something we learned previously, you find the probability of each of these z-scores and subtract them, with the bigger one coming first and subtracting the smaller. So this means I'll be taking the probability of my z-score being less than 0.41, that'll be a larger number, and subtracting the probability that my z-score is less than 0.17. Go to your standard normal table, look up both of those probabilities. You should find 0.6591 minus 0.5675. When you subtract, you get the decimal 0.0916, or there's about a 9.16% chance, a relatively small chance, that exactly 48 of the 75 in the sample will respond they have arthritis. There are quite a few steps here, but once you do a few practice problems, you should start to gain confidence in how to approximate a binomial probability using a normal distribution.